All right, hi everybody. This question was asked here, so it's problem 23 from chapter 14. I think it's 14b. Could be wrong though. So number 23 here says a 200-gram mass attached to a horizontal spring oscillates at a frequency of 2 hertz. At one instant, the mass is at x equals 5 centimeters and has a velocity of negative 30 centimeters per second. Determine the period, the amplitude, the maximum speed, and the total energy. Okay. Many ways to solve this actually. So I'm gonna do it in terms of just stuff that we know. So I'll start with the period. So I know that the period is just the inverse of the frequency. And let's see, they gave me the frequency, it's 2 hertz. So that must mean then that the period is going to be 0.5 seconds. So again, frequency is hertz. That's hertz, which is essentially the amount of revolutions, or in this case, we'll say oscillations per second, and that's related to that's the inverse of the period, which is measured in seconds per oscillation. So they're just inverses of each other. Okay. So, all right, let's do B then. It says the amplitude. So, want to find the amplitude, and you might think like, oh, um, I'm in a bind. I don't know. I haven't been given any equations with amplitude, but I can think about this. Okay. Well, I got a spring mass system. So let's see. Let's say this is the equilibrium position right here. This is 0. And here is when the spring is scrunched up like this, and then it's going to oscillate to this point right here where I'll try and draw it in a different color, where the spring is stretched out, right? Like this. And so it's oscillating back and forth. And let's just, we could pick just this random moment right here. Actually, we'll do here because they said it's negative. So whatever. At this random moment where it's moving, we're going to say it's moving, so it hasn't reached hasn't gone completely to the left just yet, but it still has kinetic energy at this moment. So say initial kinetic energy, but then it's also going to have potential energy because it's displaced some distance from equilibrium. And so eventually it's going to reach its maximum displacement. I don't know, we could say it's like right here, right? So it's at its maximum displacement, which would be the amplitude right there. And at that point, it's only going to have kinetic energy. So with that, I can then use the conservation of energy because I can assume no friction here. Yeah. So, okay, so I could say the initial energy is equal to the final energy. So initially it was just kinetic and potential. And then at the end, it's all, oh, no, not kinetic. Ooh, bad. Just potential energy when it's at its maximum displacement, right? Because it won't be moving, so there's no kinetic energy. Silly Fournier. So it's going to have that. Okay, so initial kinetic energy, we got an equation for that. It's 1/2 mv initial squared plus 1/2 k, and then the initial displacement squared. And it's going to equal 1/2 k times the amplitude squared, which is what we're trying to find. Boom. And then the 1/2 cancels out. Let's see, and then I can isolate. So I'll try and show some of the math here. I tend to try and go quickly with these videos because again, you can probably play them slower or something like that. So we won't have k. So I'm going to divide everything by k. So if I do that, again, the k divides here and it divides here. So this k is going to cancel. And then this k is going to cancel with this k, but I still got to put it under that one. So it's going to be m over k and then v initial squared plus x initial squared equals a squared. Let's see. So I know the speed. They gave me the speed, 30 centimeters per second. They gave me also the initial position is 5 centimeters per second. I'm going to convert those to meters, but I don't know the spring constant. And again, you might think like, oh no, I don't know where to go from here. But I did just figure out the period. So from the period, one of the big equations that we got from oscillating spring mass systems is that the period of a spring mass system is equal to 2 pi times the square root of the mass over the spring constant. So I can figure out what the spring constant is going to be. So I'm going to divide both sides by 2 pi. So let's see. This is going to be the period divided by 2 pi. All of this squared. That's going to equal m over k. So that means then my spring constant is m times let's see, 2 pi divided by the period squared right there. And so that's going to be my spring constant. So let's see, we can plug that. Wait. Let's we're gonna plug that in there. Again, you might just say like, oh, Fournier, plug in numbers, which I can definitely do, but that's gonna make me so. Let's see. We got m over 2 pi over the period of a spring mass system squared. So let's see. This is going to be m times 2 pi over the period of that spring mass system squared. We got v initial squared plus the initial position squared, and then a squared. So one of the reasons I did this is the mass I can see is going to cancel out. So that's going to give me the period of the spring mass system divided by 2 pi, all of this squared, times the initial speed squared plus the initial position squared, all this square rooted, because that's going to give me my amplitude. What does that look like in terms of numbers? The period we saw was 0.5 divided by 2 pi squared. The initial speed, I think it was 30. So yeah, 0.3 meters per second squared, and then plus the initial position, which is 5 centimeters, so 0.05 squared. Okay, so I'm going to plug all this in. Sorry, you'll have to wait with me for a little bit while I do this. So let's see, 0.5 divided by 2 pi, all of that squared times 0.3 squared, and then I'm going to add all that to 0.05 squared, but then I need to take the square root of all that, yikes. And so I get an amplitude of about 0.0554 meters, or that's 5.54 centimeters. I'm sure I could have just kept the centimeters, but I get paranoid and I like to convert to meters because I know those always work. Okay, so there you go. There's part B. That in my opinion was probably one of the most difficult parts, was part B. So let's see, part C then says, what's the maximum speed? Well, again, I can think about this spring mass system. I'll do it at a simple spot where it's at the maximum displacement. So I'll start that as my initial moment. And then at my final moment, I'll say it's at the equilibrium position, because as we talked about in class, we know that at the equilibrium position, that's going to be where it has its maximum speed. So those are my initial and final moments. So that means that initially I'm going to have spring potential energy, and then it's going to turn into the maximum kinetic energy at the bottom. So it's going to be 1/2 m times the amplitude squared, k times the amplitude squared, and that's going to equal 1/2 mv squared, and this is going to be my maximum speed. Again, the 1/2 cancels out. I get k over m, a squared, and then I'm going to take the square root of all of that. Again, so let's see, and that's v max. So let's see if we can simplify this a little further. I found out that the k was equal to m times 2 pi over the period of the spring mass system squared. So this is going to be m times 2 pi over the period, all that squared, divided by m. The m cancels out, and then I get a squared here. And now I'm just going to plug in kind of everything. So we got the square root of 2 pi. Well, the square root's going to cancel out everything. So I think it's just going to be 2 pi times the period of the spring mass system, which is 0.5. The amplitude is going to cancel out as well, which I just found the amplitude to be, do I want this in centimeters? Yeah, let's keep it in meters. 0.0554. Again, I'm a paranoid soul. So, and we'll get V max. So, let's see. So we got 2 divided by 0.5 is 4. So 4 pi times 0.0554. I'm getting about 0.7. So basically about 0.7 meters per second. And that is, so 70 centimeters per second. Quick little check is I can go, oh, well, 70 centimeters per second, that's a greater speed than 30 centimeters per second. So that's definitely a bigger speed. So that makes sense that it would be a maximum speed. Okay, so next up then, the total energy. So with the total energy, I haven't calculated the spring constant really. So I can pick any moment I want to in the spring mass system because it goes from high amplitude to the equilibrium position. And any one of those moments I can choose to calculate the total energy. So I'm going to choose something easy, which is at the equilibrium position where I know it has only kinetic energy. So the total energy is just going to be the maximum kinetic energy point, which is 1/2 mv squared. I already calculated v over here. So that's going to be 1/2 times the mass. Did they give me the mass? They did, 200 grams. 200 grams. Did I? Oh, no, the mass always canceled out before. So 200 grams, so that's 0.2 kilograms times the speed, which I just found, which was 0.7 squared. So what does that look like? 0.7 squared times 1/2 times 0.2 is 0.1. So I'm getting about 0.049 joules. And there you go. There's the maximum, the total energy that it's playing with. Yeah, so a lot of energy equations. Again, I think part B was quite tricky. Okay, so hopefully that helped. Thank you. Bye.